Well, I guess you were wondering, would we ever get back to Newton's work? Kinematics, here it is up the top, aka motion problems. We're going to be talking about motion in a straight line here. We'll get on to that in a minute. I just want to revisit all the stuff from before. Can you see it here? Our distance against time plot, our easy one, where our velocity was delta S on delta T, which was 160 over 2, which is 80 kilometers per hour. Okay, so then Newton's dilemma. Well, here we go. When the velocity, or the displacement time plot, is a curved line, what do? Well, he wasn't happy. Just go back over this. Don't want to bore you, but he wasn't happy with doing this sort of caper here between 2 points on the curved line and getting our delta S on delta T. He said this was the average velocity because the body wasn't actually following that displacement time pattern. It was going along this curved line. So here's our error in here. Okay, it was not a straight line plot between those 2 points in time, and he didn't want the average velocity. We're going to visit that again and do some problems on that. So what did he say? Well, let's bring this point closer and closer. Okay, and so there's smaller and smaller gap in there, and see what we could do with that. And he said, well, I don't want any gap. I don't want any gap. So we said in an earlier presentation, let's say we were working at the point in time t equals 5. The limiting position of those chords as they came in would be a tangent. So we needed the limit as the slope of that chord as you got closer and closer to here. And we had a first principles definition there. Do you remember it in the end? F dash x equals limit as h tends to naught of f of x plus h. Take f of x on h. Good stuff. Okay, now what Newton did, of course, was to do this all in S land, S dashed of t, because look at our graph, S and t. Oh, I've done it again, haven't I? I've done it again. What did we say? This was going to be centimeters and seconds. Shouldn't leave that out, Huddy. Okay, not to worry. Okay, so he did it in S and t land here because he was looking at the application to motion. Now, that brings you up to speed with what's going on here. Let's go and look at his maths again down here and see what you think. Oh, gee, this is bad, isn't it? Look, I've done this again. Here we go. I've copied that graph and I've forgotten to correct it. Okay, I think it gets better later on. I've got a few other graphs and they're all labelled. Anyway, so let's have a look now. If you were going to do it in general on this plot, let's say we're starting at a point here, we don't know, just call it T, T1 maybe, and then T2 here, T2, this point would be, T1, S of T1, all in the notation of S and T, T2, S of T2, in brackets there. Okay, so now the slope there of that chord, delta S on delta T would be S of T2 minus S of T1, that's the delta S step, and over here T2 take T1 delta T step. So now our average velocity would be delta S on delta T, and that would be equal to S of the second point minus S of the first, just averaging it across that interval. Okay, so that's in S and T land where Newton started, and we generalised that to Y and X land. Okay, so what happens to all of this as we come closer down here? We're going to tend to tangency. So we're going to say the instantaneous velocity is the limit as our delta T tends to naught here, as delta delta t tends to naught of our s of t2 take s of t1 over t2 take t1. And we're going to call that, the velocity is the instantaneous rate of change, so that's going to be the derivative, s dash t or ds by dt, linking up with what we've done. Okay, let's do it in a slightly different notation. So let's go and do all this again in a slightly different notation. T and t plus h's, all that stuff, because that's commonly used. So if we start at a point here, t, this will be t, s of t, and go out h, let's say. So this will be going out a distance of h, because this is becoming the convention. This would be t plus h, s of t plus h. Okay, so there's another way of writing it, and our delta s and delta t there. So our average velocity could be thought of s of t plus h, take s of t over t plus h take t is just h. And then our instantaneous velocity, which is the derivative, is the limit as h tends to naught of that. Okay, so it's all the same stuff. It's very important that you get the difference between average velocity, and when we take the limit of the slope of that chord, we get the instantaneous velocity. Now that's Newton in a nutshell. Hey, I don't think you can put a person in a nutshell, can you? Oh, don't worry. Anyway, that's his work in a nutshell, and let's go down and see what he then did, because Newton was responsible for a lot of equations for linear motion, and he studied this sort of stuff extensively. Let's have a look at the work. It's exciting. Okay, so here we are. Here's what we've just done. And the screen clippings in this presentation come from two sources, Hayes and Harris, and also Pearson's textbooks. So you might have a look at both of those. Okay, so here's our definition that we just established. The average velocity is taking the two displacements away and divided by the time. This made Newton unhappy. He was unhappy with this averaging effect. Okay, the average velocity. So he did this transition. Let's have a look at the limit as h tends to naught. So that's the instantaneous velocity, or now we say the derivative is the limit of this average thing here. Notice we put in t plus h and t instead of t2 and t1. So this is the idea of the limiting position of the chord, giving the average velocity is the tangent. And so if we can find the limit of that delta s and delta t expression, then we have it. Okay, that's our notion. All right, let's keep developing it, keep reinforcing all these ideas now. So here's what we're going to do. We're going to imagine we're in a physics lab, and we're going to keep the motion in a straight line. You might say, well, why? Very few things travel in a straight line. And the reason for that is we're going to start talking about velocity. And velocity talks about having a magnitude, a size of the meters per second or kilometers per hour or something. And also we like to talk about where it's going, its direction. So we're going to have to make it simple. If you don't make it in a straight line, you have difficulty explaining all the direction changes of a body, because they can be minute or large. But we're going to do this. We're going to imagine a body is moving on something like an air track in a physics lab. Okay, so we're going to start measuring at some point O, the origin. This is not the origin of the motion. The body may well start back here somewhere. But we're going to measure this. How far away the displacement, or the point, the body, point P, is away from the origin, the displacement of that point from our measuring origin. So this is the start of the meter ruler or something. There. And if it's back there, it's going to be negative displacement. over this side positive. So we're going to get some signs in here which are going to be important in speaking of velocity. So a positive velocity is going to be to the right and a negative velocity is going to be to the left. Okay, positive and negative displacement as well. Okay, the same thing. So we're looking at measuring the displacement of that point away from the origin, our starting point of measurement. And so this is this is an S-axis. Okay, an S-axis, because we use little s to measure displacement in motion problems. Okay, now if f of s of t is greater than naught, it's over on this side, isn't it? Coming out here, so it's located to the right. If s of t equals naught, the point is at the origin of measurement, and if f of s of t is negative, it's over on this side. It's located to the left. So we're setting up a little system for analysing simple linear motion in a straight line. And Newton did a lot of work. If you're into physics at all, he's got a set of linear motion equations for linear motion. Okay, we're not going to go so much into those. We're going to be looking more at working out velocities from displacement expressions and so on. Okay, let's go down and have a look. Because the burning question that you want to ask Huddy is, say, Huddy, how would you get a displacement expression? You know, you've got that graph back there and we're trying to find S-T and all that. Could you get a displacement expression? Let's look at the origin of this work, the experiment. Okay, so this is our experiment up here, which a body is moving, let's say, along an air track, and it begins over here. Okay, and that's actually to the left of the origin of motion. This is the origin, no, not origin of motion, or just origin of measurement. And here the motion is starting to the left. Okay, the body's starting to the left. T is naught. It's at -3. We can call that centimetres. Let's say it's an air track. And then at T is 1, it goes through the origin of measurement. T is 2, it's 5. At T is 3, it's 12. T is 4, it's 21. So we could actually do that experiment in the lab. Okay, and then we could summarise our results. Well, that's our data there. 0, 1, 2, 3, 4 seconds, and there's the displacement. Okay, so now let's see what was happening to that body. Is this a constant velocity? I think you can see it's not. Well, you can see these gaps here, can't you? Every second it's moving more quickly. Okay, bigger gaps, delta S on delta T. The average velocity between those points is getting greater. So what would you do? What would Newton do? Well, I think the next thing you'd do is plot the data, and there it is there. So there are our results plotted. Okay, and what's the next thing you'll do? Well, you don't want to find velocities by drawing tangents, do you? Too inaccurate. Okay, so what would you like to do? Use calculus, but to use calculus you've got to fit a model. You've got to fit a mathematical model to the data. Now in Newton's time that's a lot more work than what it is now, because if you were in the lab you'd probably use a graphics display calculator, okay, in stat mode, and try and fit various curves to it. Okay, and you come up with a perfect fit for this quadratic, because we're using just this nice easy example to show you what's going on. So the body started, where was it, the displacement? See, I got it right, look, I got it right. I put the units in. Oh, that's good, finally got it right there. So here, where did it start? At a displacement of -3 centimetres. Then at 1 second it was at 0, the origin of measurement, and so on. So we've plotted it, and here we have the function. What is the big deal now? If we can do that, we can say the instantaneous velocity is s-t, or ds by dt, and that is equal to 2t plus 2 from our x to the n rule, remembering y equals x to the n implies y dashed equals nx n minus 1, or dy by dx, whatever, any of those notations. So there it is there. Look at what we've done. So we can find the instantaneous velocity at any point. So how fast was it going at t equals 2? Let's read it here. There's t equals 2. Fairly steep slope of tangent. Put t as 2 in here. 4 plus 2. It was at that instant going at 6 centimetres per second. And so that should be the slope of that if we did it. You should have a slope there of 6. Shall we play with that? Let's have a look, see how good it is. See if I can do it. So there's our point t is 2. That's the point 25. And then if we come out here, this is our tangent. Does it hit another point? Oh yeah. 3, oh, my tangent's, yeah, 310. Yeah, 310. Let's see how well we can do it. This is inaccurate though. Remember, you don't do it this way, use calculus. So the velocity at that instant is supposed to be the slope of the tangent. 10 take 5 over 3 take 2, 5 over 1, no. A near miss. This is inaccurate, isn't it? See, I tried to do the construction here. I messed it up. Here it is down here. This is what we want down here. Put in t is 2. 2 times 2 is 4, plus 2 is 6. It's supposed to be 6 centimetres per second. Okay. Alright, let's just look at this notation here. The centimetres per second. If you look at velocity, it's a change in displacement with time. Okay, well actually, let's put here the limit is delta t tends to 0, delta s on delta t. So what you're looking at in units are centimetres divided by seconds. Or you can think of that as centimetre s neg 1, because the s is in the denominator, and 1 over s in power notation, power rules, is s to the neg 1, isn't it? Okay, so that's where that comes from. We haven't done much physics. Centimetres per second. You can also write it as this, if you like, per second, like that. So there's two different ways there of doing it. So you're getting the idea. We now want to see if we can get from experimental empirical data a plot and then a formula, so that we can actually do calculus on this. Okay, get our derivative. Now it's getting very accurate. We don't want an estimate like this, if we can possibly avoid it. We do therefore need our model. Okay, come on down and let's develop it a bit. Here's something from Pearson's textbook now. I'm going to look at a more complicated displacement function. You can see here it's a cubic. What else can you see about this graph? Look carefully. Oh, they've done it as well. Left off the units here. Oh well, that's a bit naughty, not to worry. I've been doing it for a couple of presentations now and correcting myself each way. So just you watch that. We need units for both of these axes, really speaking. Okay, here we have a displacement function. Let's see if we understand it. Here it is, time at 0. It is at the origin. Displacement is 0. It's increasing at an increasing rate there, so it's still Newton's problem. It's not a straight line displacement time graph. At t is 1, it is 4, let's say, meters. Well, we could call it centimeters. Centimeters, and this is seconds, let's say, keep it like that. So it's 4 centimeters away from the origin. Then at 2 seconds, it's 8, here, 8 centimeters away from the origin. Oh, then it must stop, because it's coming less. It's getting closer to the origin, isn't it? Or what's happening here? Yeah, so at 3 seconds, it's back to the origin. So this must have stopped here. Must have stopped at that point. And, oh yeah, that'd be right. Look, the slope of the tangent, that's the instantaneous velocity. Slope of the tangent is 0, parallel to the t-axis. So it stopped and now it's coming back. At 3 seconds it's back at the origin. It's coming back to the origin here in the displacement. Okay, so that's interesting. And what would you say? Well, the velocity here, the slope of the tangent is positive, and now the velocity is negative. If you were to draw that, what have you got? It started there at t is 0. At t is 2 it went out to 8 metres. So this is an S displacement line. So at t equals 2 is out at 8 metres. And then as t equals 3 it was back here. So could we plot that? It went out, and I'll just put around there and went back. It actually went on the same straight line, didn't it? Because this is linear motion we're talking about, keeping it simple. But we could track it like that. So when it turned around, it must have stopped and then came back. So this is going this way was positive velocity. Going this way is negative velocity. Getting an idea of what the graph means now. Okay, let's have a look at plotting the velocity graph and see what it looks like. Well, what's the velocity function? It's the derivative. And if we plot that function, it's negative 6t squared plus 12t, which says, well, okay, it starts off with a positive velocity and increases, then gradually, here it is, increasing, then it gradually slows down, and the velocity is 0 at time 2, which is what we said. Then it comes back to the origin, so that they're all positive velocities here, and then the velocity is 0, and these are negative velocities because it's travelling back, and at t is 3 it's going pretty fast. It's oh, I've left the signs out here, neg 5 and neg 10. It's going pretty fast through at 3, but at 3s was 0, and the velocity is neg 10, well, about neg 7.5 centimetres per second. You're getting the idea. We're trying to understand our graphs in terms of our motion on our air track, or whatever experiment we're doing there. And what's happening here? Well, hang on, this raises a question, doesn't it? This raises a question. Here the velocity is decreasing. Starts off very fast in a positive direction. It's increasing to there, and then it's a maximum there. Starts off slowly in a positive direction and is gradually increasing up here. But how fast is it changing? These tangents are getting less steep. Does it make sense to say it is getting to a maximum and then it's coming down again? Hang on. What about delta V on delta T? Does that make sense? I mean, here the velocity is increasing up to there and then decreasing. Is this worth looking at? The change in velocity with time. What's that called? If you are looking at how your velocity is changing, let's say you're going 80 kilometres an hour. You go from 80 to 100 kilometres an hour on a highway. What's the change? 80 take 100 take 80. Let's say you do it in 2 minutes. So that's 10 kilometres per minute. Change in velocity. Oh, hang on, that's kilometres per minute divided by minutes. This is acceleration, isn't it? How fast is your velocity changing? We say is how fast you are accelerating. The acceleration is kilometres per minute squared, or changing kilometres per minute for every minute. That's acceleration. Can we do that? Let's get rid of this and say, well, okay, if we have a velocity time plot, then we might be interested in how it's changing. Okay, what's happening to the velocity there? What's its derivative? Could you do that? The slope of these tangents, slopes will equal the derivative of velocity, which is the acceleration. And the body, what's happening? Well, it's going up to a maximum velocity of whatever that is, 6 or something there, but it's accelerating, what, positively, but at a decreasing rate here, in here. Right, all of these slopes are getting less. But we could talk about how fast the body is accelerating. And then coming down here, the slopes are negative. So the acceleration is negative. Something is pulling the body back. Okay? And then if it keeps doing that, coming down here, more and more negative acceleration, because the slopes of the tangents are negative. We've got positive acceleration here. Okay, and then negative acceleration. And here, no acceleration there at that turning point. V dash t, so for the tangent to velocity graph would be 0. So that might explain why the body did what it did. What did it do? Let's go back and do it again. It was going out, it went out to 8. This is S, so this is 8 meters, 0 meters. This is T is 0. This is T is 2. So it went from T is 0 with positive velocity and positive acceleration, but the acceleration ended up at T is 1 being 0, and then it started to be negative. So somewhere in here at T is 1, don't know what the displacement was there, at T is 1, the acceleration stopped being positive and became negative. Somebody was retarding the body, holding it back. And so in this interval, the body slowed. Eventually, the acceleration was continually negative in there, and it caused the body to stop and reverse after t equals 2. Now this is getting interesting, isn't it? Come down and have a look at the graph of the acceleration function. Here it is. The acceleration function was positive. Okay, positive values for the acceleration, which is the derivative of the derivative, or s double dash 2. You can do it again, because the journey is s of t. Let's find its derivative, the rate of change of displacement at the time, which is velocity. And if we did it again, that would be the derivative of velocity, which would be the acceleration. Now, could you do it again? Could you do it to this one? I suppose you could, but it wouldn't have any everyday meaning. You can keep going and keep differentiating or finding rates of change forever. But is it appropriate beyond this second derivative? No, it's not. But it is useful here, because you can see at t is 1, the acceleration started to become negative. By t is 2, it actually slowed the body down to a stopping point 8 meters from the origin, and then because it kept being negative in this region, the body then went back to the origin at t equals 3. So this was a v equals 0 point on the other graph, because after a positive acceleration to a maximum velocity, I think at 1 it was, it then turned negative, so it changed the force on the body and caused it to go back to the origin, slow down at 8 meters and stop at t equals 2, and then go back to the origin at t is 3, back to O, and accelerating to the left quite rapidly. We're going to do it more easily than this, but it's interesting if you can get your head around the actual experimental results in a graphical form. Okay, let's go down and have a look at some of this stuff. Here we are. I'm going to summarise it all now. So, from Pearson's here, displacement function, an interesting one. You can find the average velocity, or you can find the derivative. the instantaneous velocity. But hey, we can do it again. If we have the velocity function, we can find the average acceleration, the rate of change of velocity with time. Makes sense to play it again, Sam. Okay, and if we want the instantaneous acceleration, we have the same thing done again in velocity land. Can you see it? Look at the expressions. S of t2 take S of t1 over the difference in time. V of t2 take V of t1 over the difference in time. And here the limit of that expression and the limit of this expression using t plus h minus t. Same ball game here, only we're doing it with an x function. Are we going to do it to acceleration? No, there is no actual practical meaning. No practical meaning. It would mean it's the rate of change of acceleration with time, which isn't any quantity that we're particularly interested in. But we are interested in change of displacement with time, which is called velocity, and then the change in velocity with time, which is saying how fast we're speeding up or accelerating. All right, there's a lot to digest there. You might like to pause the presentation and just have a look at the definitions there. The graphs are from Pearson's and the definitions here are from Hayes and Harris. So it's a good combined effort there. All right, let's go on now and have a look at what we can actually do. So here are some problems that would be required in this course. Okay, we start off with a displacement time expression. Find the average velocity from the time interval t is 2 to t is 5 up here, and the average velocity from t is 2 to 2 is 2 plus h, and then comment on the derivative. Okay, so you might like to just think about that for the minute. Well, let's have a look at that in detail now. Let's try and get the average velocity. So the average velocity from before, as you know, is s of 5 take s of 2 over 5 take 2. From t is 5, from t is 2 to t is 5. So that's good. Let's work that out now. So putting the numbers in to the original displacement expression, 5 and 2, gives us 15 take 25, subbing in to here, and then take 6 take 4. So that's our change in displacement, and then dividing by 3. So it's -4 meters per second. Average velocity, using this notation, 2 and going out to 2 plus h, would be s of 2 plus h take s of 2 over that. So let's draw a graph of this. What are we doing here? T, and this is s, this is meters, don't forget that now, and seconds, and 3t take t squared is, what is that? That's, let's try and have a look at the graph of that. That's 3, so it's going to be something like this coming down there. So what we're doing is taking a point at 2 and then 2 plus h and doing our chord, aren't we? So there's a difference there of h. So it's doing that starting with an actual point, 2 plus h, s of 2. So we have to put 2 plus h back in our function. So it's 3 times 2 plus h, take 2 plus h squared, and then putting 2 into our function, which we calculated before. Okay, all over h. And so doing the algebra on that, just expanding this bracket. First of all, let's multiply these out. 6 plus 3h, take, and the square of this is 4. Twice the product, 4h, but it's take. I'd like to do this in steps, so got to be take 4h, and h squared with the take out the front, subtract is neg h squared. So we're going to get this expression. I think it would be good to put out a common factor of h, neg 1 take h, over there, and we can cancel with a proviso h is not equal to naught, and therefore we've got neg1 take h meters per second. And that would be our average velocity, the slope of the chord there. Okay, what about if we take the limit as h tends to naught? We're approaching tangency, aren't we? This is going to give us the slope of the tangent, which is the limiting value of the slope of the chord. So subbing in h is naught in there, we get neg1 meters per second. So the slope of the tangent at t equals 2 would be neg1 meters per second. And that would be our instantaneous velocity. Okay, so we want to be able to do it in all different ways here. And that gives you an idea of the sort of questions you might be asked. Let's go down, and I want you to try and do that for a couple of problems now. Okay, here are a couple from Hayes and Harris, question 1 and 2. Try and go through the same sort of process now as with that example, so you might have to toggle back and just check it and see what you think. If you don't like all my writing over it, go back a little bit further until it's just a plain problem before I start scribbling all over it. Okay, pause presentation, have a go. I want you then to have a look at the solutions. There's question 1. So just check your numbers there. And then question 2. Okay, are you ready? Let's go on and have a look at the next ones. I want you to do the same thing now with the velocity function here, because it's the same idea. Average velocity, average acceleration, instantaneous acceleration. Okay, so just as a different function to work with. Okay, so go through the same process. This time we're starting off with a velocity, and the acceleration is the rate of change of the velocity. Okay, so I'll bring these two questions up for you to have a go. Question 3 and 4. See what you think. Pause it and have a go. Come down now. Question 3. Remembering, as soon as you find that limit, it's a instantaneous value. You might check this here. This is the trick to simplify this stop line so we get an h in it. It's multiplication by the conjugate, isn't it? So you create the expression a plus b by a take b, which gives you a squared take b squared, which enables you to get rid of the square root here. So you might study that, you might have to talk to your teacher about that one. Okay, let's look at question 4. Yep, just a discussion there of the meaning of those expressions. Okay, building up some confidence, I hope. Let's go on a bit further, and there's not much more to do. We've got all the key concepts covered so far. Okay. Here we are. Let's look at a summary of what we've done. The velocity is the instantaneous rate of change of displacement, or the derivative of the displacement function. The acceleration is the rate of change of velocity, the derivative of the velocity function, or the second derivative of the displacement. Now, just keep in mind here Huddy's description. Oh, that's not a very good circle. Don't like that. Hang on. Just draw it over here. Bit hard to draw on screen. Remember, we've got derivative, and you can think of that as slope of the tangent, or dichotomy here, the instantaneous rate of change. And that's what we're doing here. Big emphasis on the idea of the instantaneous rate of change, because it's motion, and the instantaneous rate of change of displacement is the velocity at an instant. That was Newton's challenge. And then the rate of change of velocity is the acceleration instantaneous acceleration at a point. How fast are you actually speeding up at that point? Alright, let's go on with a bit of other stuff now. This notation, S of naught, V of naught and A of naught, means, as with usual functions, in place of t, you're putting t as naught in each of those spots. So that's what's happening initially, because t equals naught means at the start. When you're starting the clock on your experiment, at the start, and that's the word initial. Okay, so just remember what we're doing. The origin is not necessarily where the body starts, it's the origin of measurement. That's where our displacement measurement starts from, and it could be going positively there, or it could be going negatively. The body could start anywhere along your track there. Okay, so now we're going to talk about how fast it's going, what direction it's going, how far it's travelled, and all that stuff. Alright, so let's have a look at summarising our track and things like that. Signs of the displacement. The displacement is 0. The point is at the origin of measurement, at O. If S is positive, it means it's gone to the right. If S is negative, it's gone to the left. So we're just formalising here now our system for analysing this linear motion. It's going up and down a straight line track. That's all we're doing, so we can easily discuss velocity as positive or negative. Velocity requiring a magnitude, how fast it's travelling, and a direction. So now, what about V of t? If velocity is 0, it's instantaneously at rest. It stops somewhere. It stops at a point in time. If the velocity is positive, that's s dash t, so it's moving to the right. Okay. If the velocity is negative, it's moving to the left, because s dash t would be negative. Okay. Negative rate of change there. So let's have a look at acceleration then. You might note these down yourself for later on if you don't think you're going to remember them. Some of these points, it's worth going back and summarising them. What about the acceleration? If the acceleration is positive, that's what that means. Velocity is increasing. Oh, we know that because A is dv by dt or v dash t, and if a derivative of a function is greater than naught, the function is increasing, isn't it? From our last discussion of functions in general. A function is increasing if its derivative is positive. So if acceleration is negative, velocity is said to be decreasing because its derivative is negative. And that goes back to our function. F of t is increasing if its derivative f dash t is greater than or equal to naught. Okay, what if the acceleration is 0? Velocity will be a maximum or a minimum. That's from an earlier presentation as well. If the derivative of a function is 0, it implies the function has a local max or min. Okay, because v dash t is the slope of the tangent or the instantaneous rate of change, and it's 0, so it's a stationary point, a max or a min. Alright, let's go down and summarise a bit more some of the phrases used in describing motion to do with time, displacement, velocity and acceleration. Initial conditions means time is 0, just done that. At the origin means displacement is 0, the origin of measurement. Stationary means it stopped, velocity is 0. Reverses also means the body has stopped. Remember the one before, t equals naught, it was at the origin, then t equals 2, it was 8 metres out, and it stopped there, so v would have been naught. This is always a displacement graph here, and then it came back So to come back reversing direction, it must stop. Okay, it can't go in the opposite direction without instantaneous point of stopping, or stationary point. So here it reverses, means v is naught. Maximum height, same thing, because the body's going to go up and then come down again. So at this maximum height here, okay, ds by dt, v must be 0, must stop before it can come down. So a variation of the same thing. Constant velocity means acceleration will be naught. Why? Because if v is constant, v dash t is naught, that means a is naught, no acceleration. Maximum minimum velocity, the derivative of the velocity must be 0, as it must be for any function. It's going to have a local max or local, excuse me, local min. Its derivative must be 0. The tangent to the curve at that point would have a 0 slope. It would be parallel to the x-axis. That sort of idea. Just reinforcing all of that. Okay, are you ready to actually attack some problems? Let's have a look at some ideas now. So let's bring in speed. Now speed is irrespective of direction now. Is actually, we use a big S usually, and it's the size, modulus or absolute value of the velocity. So we're not interested in its sign as to whether it's positive or negative. Not like we are in velocity. Which way is it going? Which way is it going is what we don't want to know with velocity. It's not just centimetres per second, but positive or negative. This linear motion going up and down this track. Okay, so no sign for speed. We're not interested in which direction it's going, just the size of it. Okay, let's have a look at an idea of when would the speed of a body be increasing. Okay, the speed is increasing. Now the velocity is increasing. Let's just distinguish this. V dash t has to be greater than naught for the velocity increase. Usually be equal to naught. V dash t less than or equal to naught is decreasing. Now, this takes account of it as a mathematical function, and they are our definitions. But speed is a bit different, because if, for example, the velocity is getting more negative, we say its rate of change there, less than or equal to naught, it would be decreasing. But it might actually be speeding up in the negative direction. So the speed could be increasing, but the velocity decreasing. Let's see if we can do this. So the signs of velocity and acceleration are the same, both positive or negative. The body will speed up. Let's see if we can get it over here. The velocity function here is what? It's positive all through this region. Okay. And what happens? Okay, well, the acceleration function down here, if we try to match it up, the acceleration function is positive just in that region, okay, and decreasing to 0 here. So at 1, the acceleration is now 0, and from 1 to 2, the acceleration is down here, it's negative. Okay, what's that going to do? It's reducing the velocity of the body, because the body has a positive velocity, but the force being applied to it now is in the opposite direction. It's opposing the motion. It's a negative acceleration. It's going to slow it down. So the velocity is 0 at 2. This negative acceleration is finally 1 and slowed the body down. Now, from now on, what do you notice? The velocity is going to be negative, and the acceleration continues to be negative. I should just go from here, from 2, because the body stopped. The acceleration is negative still. So now in this region, the body has a negative velocity, okay, below the axis, and the acceleration is also negative. So the velocity is going to get more and more negative. Hey, it's going to speed up. Okay, it will speed up in that region. Okay. Now, in that region, though, the velocity is decreasing. This is a problem. Why? Because the acceleration, the derivative of velocity, is negative. Any region where v dash t is negative means the velocity will be decreasing. It's getting more and more negative, which on a number line mathematically, when direction is taken into account, is a decreasing value. Okay, getting more and more negative. V dash t is less than naught. But it is actually getting more and more negative, and that means its speed, the size of the value at which it's travelling, if you like, not its sign, it's actually speeding up. Okay, what about v of t and a of t being opposite, and the speed will be decreasing? Let's get rid of all this and try again and see what's happening. Alright, so in this region the velocity is positive and the acceleration is positive. Then we turn that force off, if you like. Acceleration is 0, no force acting, and it's got its maximum velocity. When we have the next force, which is opposing the motion, it's negative acceleration. When that is operating, look at what happens to the velocity. Okay, so it's coming down, and so this is where the velocity is still positive, but in the same region down here, the acceleration is negative. What's that going to do? It's going to stop the body. It's going to slow it down. Okay, so in this region, there's the speed. The speed is decreasing. Not worrying about its sign, just the fact that it's getting less and less in size. The speed is decreasing because we have the opposing signs of velocity and acceleration. It is easier to understand if you understand a little bit of physics or Newton's second law. A of t, it results from a force on a body. From a force on a body. So, if A of t is greater than naught, it implies the force acts in a positive direction, and if A of t is less than naught, implies the force acts in a negative direction. So if you've got a body moving along with a positive velocity, v positive, and A is negative, that implies the force is opposing it. So that's a little bit of a physics background to the idea. If the signs are the same, the body is speeding up because the force is in the same direction as the current motion, but if they're opposite, then the force is opposing the motion and it's going to slow the body down. Alright, so that can seem quite complicated. Try and get your head around the idea of what's happening there. We're going to do it in much simpler terms right now. So let's have a look at some simple ways of handling this sort of stuff. Okay, so here we are. We've got a displacement expression up here. T is in seconds and the displacement is in centimetres. Okay, find expressions for particles' velocity and acceleration. Draw sign diagrams for each of them. Okay, well there's the displacement. Derivative of t cubed, 3t squared. Derivative of negative 3t is 3. Derivative of constant is 0. Okay, and that's because the velocity is the derivative of displacement with time. So factorising the 3 outside a bracket, and then factorising that difference of 2 squares, we've got t equals neg 1, putting it equal to 0, or t equals 1. Let's draw a sign diagram. So there's the t-axis. See here, we would hash it usually because t can't be negative, so t is neg 1 is not required. So put in t as 1, put in 0 in this region, you find it's positive. Put in 2 in this region, you find the displacement, put in t, it's negative. Put in 2, it's positive. So that's the sign diagram for our v of t, our velocity function. Okay, Now let's do our acceleration. So the derivative of this line up here is 6t, derivative of -3 is 0, so t equals 0 is the only point, and we can't have negative, so hash that in, and sub in a value from here like 1. The acceleration is always positive, so this is the acceleration. Okay, so we'll come back and compare those in a minute. Let's have a look at the second point, find the initial conditions and hence describe the motion. So at t is 0, subbing in 0 into the displacement, you get 1, into the velocity you get -3, acceleration you get 0. So the particle is where? It's 1 centimetre to the right of O, moving to the left at a speed of 3 centimetres per second. So I could do that here. 0, it's 1 metre, 1 centimetre there at t equals 0, and it's moving, it's got a negative velocity, so it's starting here and moving off there at -3 centimetres per second. Okay, and if you want the speed, then there's the velocity, and the speed, big S, is just 3 centimetres per second. No positive or negative there. Okay, describe the motion of the particle at t equals 2. So let's put t as 2 in. Displacement, velocity and acceleration. So the particle is where? Let's have a look. There at 2. So at 2 it's 3 centimetres to the right. And what else have we got? Velocity is 9, so it's heading off here now, 9 centimetres per second, and the acceleration is 12 centimetres per second. Alright, so it's going to get faster, isn't it? The acceleration and the velocity in the same direction. Okay, so we would say the speed is increasing. Okay, let's go down and keep going. Find the position of the particle when changes in direction occur. Changes in direction. Changes in direction is when the velocity is 0. You've got to find when v of t is 0. So that was at t is 1 and t is -1. Can't have negative time, so it's only t is 1. So it stops at t is 1, and you could draw a sign diagram. Let's just go back up and here it is up here. There it is for the velocity. Changes sign only at t is 1, and so it's going to stop there and change direction. It was going negatively, now going to go positively. And you could find when that happens by subbing 1 into the displacement expression. And it is 1 centimetre to the left of O. So let's try and put this on a diagram here. This is a displacement diagram, little s. I think they should be labelled. So here we go. Where does it start? I like to put it differently. T is 0, starts there. At t is 1, it's there. And then that's it. So put under the number line the points in time at which it is at that displacement. We said it starts at 1. The key point when it stopped was at t is 1, and it was -1 metres to the left. So here's our little plot. Here, this is a good point. The motion is actually on the line, not above it. As shown, we want to separate these two. It's going up and down the line. Okay, not above it. It's actually, this is the air track, if you like, down here, but it's a displacement line there. So now, if you wanted to keep going in time here out to the right, the displacement will just get bigger and bigger, and so with the velocity, because we've said from back up here the final for large t, acceleration and velocity are both positive, so it's just going to keep speeding up. Okay, when is the speed increasing? It's when v of t and a of t have the same sign. So let's go back up here. It's getting a bit messy. Let's just scrub this out now. That's v of t and a of t. In this region, they don't have the same sign. Acceleration is positive and velocity is negative. So that's why it was travelling to the left with a positive force going to the right, positive acceleration, so it stopped the body at t is 1. Then the body had a positive acceleration, and of course acceleration was a positive velocity and a positive acceleration here, because acceleration is always positive. They matched, so it's going to speed up after 1. So it's important to go up and look at the sign diagrams for that matching up if you want the speed increasing. When is the velocity increasing? That is also, well, let's have a look. We don't have that here. It's coming up in a later problem. When is velocity increasing? When its derivative is greater than or equal to 0. So that is for all time, isn't it? The velocity is increasing. Even when the velocity is travelling negatively, it is slowing down. Its rate of change is decreasing. So here it's always increasing the velocity. Okay, have to get your head around that one. Let's do some problems, try and copy down what's going on there now. So here are a couple, question 1 and 2. You can see these are from Hayes and Harris now. Let's have a look at question 3 and 4. One more and then we'll look at the solutions. Question 5. Let's go on now and look at some solutions. Question 1. Look at question 2. Question 3. Question 4. Question 5. Okay, I've added some from another version of Hayes and Harris books there. 2 more, 5 and 6. Now look at this hint now. When I ask you for the total distance travelled, you must have a motion diagram, so you must find when v equals 0 and find the displacement at those 2 points so that you can do your motion diagram. Okay, so S of t, origin, find where it stops and goes round and so on. Okay, so this sort of thing, and then you've got to add up all the distances. So keep your wits about you for that one. Okay, look at the solutions to those then. These diagrams are very, very important. If you're going to work out the total distance, you must find those stopping points. It reverses direction there. Okay, a couple more, this time from Pearson's. I've cut these out from the section in chapter 11. These two were mixed in with other problems, so I've separated them as motion problems. So have a go at those two as well. Slightly different approach there. Okay, let's look at the solutions to those. Graphs all under each other. We'll come down to the graphs in a minute. See if we can get them on there. They wanted you to draw them all under each other. Something like that. Okay, and the other one then. Oh, finish that off, sorry. C, D and E. and then 21. And that's it for motion problems. Now, that's a very interesting area. I hope you enjoyed it with Newton's work and following it through, because that's not a bad way of thinking about the origins of his development and discussion of calculus. All right, we're going to do more calculus coming up, so I hope to catch you in those presentations. But for now, it's cheers from me.